So we're now ready to define the Plücker embedding, which puts this Grassmannian into some projective space, and we use exactly these alternating tensor products. So the Plücker embedding is just a map from the Grassmannian into this big projective space, which takes this linear span of k vectors and sends it to the class of this wedge of v1 up to vk. And so what explains this number here? Well, this wedge here is contained in this alternating tensor product, and we have seen that this is a space of dimension n choose k, and we can write down a basis for this, enumerate it in some way. And so the recall that this projective space is of course always this minus the origin divided by an equivalence relation, and then there was this shift in dimension because you divide by scaling. So this reduces the dimension by 1. And so this is the definition of the Plücker embedding. And with the preparations that we had in the last video, it's now easy to see, first of all, it's well defined because this is a non-zero entry of this vector space, as we have seen, because the vi being linearly independent means this wedge product is non-zero. And it's also well defined in the sense that if you choose a different basis here, then we had a lemma which told us that these things are linearly dependent, so they give the same element of this projective space. Moreover, so this was kind of one direction of the lemma, and then we had the reverse direction, which said that this thing actually uniquely characterizes this linear span, and this shows that this is actually an injective map. And we call this thing the Plücker embedding, and it allows us to represent this as a subset here. And the homogeneous coordinates of the image of such a linear space, so these n choose k homogeneous coordinates, these are called the Plücker coordinates, and they're exactly the maximal minors of this matrix here, which consisted of these k spanning vectors. And yes, so we consider this as subset of this projective space, and then in the following videos we're going to see that this is indeed a closed subset. For now, let's just look at some examples. So we have already seen the Grassmannian of one planes. This should of course give us back exactly the definition of projective space, because this was defined as the space of one-dimensional linear subspaces. And well, we see that what does the Plücker embedding do if we have this one-dimensional space spanned by some combination of these n basis vectors? Then it's just sent to this thing here, the same vector in wedge 1 of k to the n, which is just isomorphic to k to n itself. And then if you choose the same basis as before, then the entries in this k to the n are then exactly go to this column vector or this row vector a1 up to an. So we get back from this vector here exactly the element in this projective space that we expect. So somehow this shows that in this case for k equals 1, this map is actually a bijection, and it gives us a bijection between this Grassmannian and the projective space as desired. Maybe a bit more interesting, so let's look at Grassmannian of 2 planes in 3-dimensional space, and then we can choose such an element. So for example, let's say we take the linear span of e1 plus e2 and e1 plus e3, right? So this would be these would be these 2 column vectors here. And well, what we do is we take this wedge product and we can expand it as we have seen before, and it is expanded exactly as this sum of 3 terms here. And you see the coefficients are -1, +1, +1. And so f of L is then just given by this vector here, -1, 1, 1, in this projective space. And we can see the coordinates of this vector are exactly the maximal minors of this matrix here. And if you choose a different basis of L here, I mean, for example, you could add this vector here to the first vector, this would still give the same linear span, then this change of basis corresponds to some column operations on this matrix. And as we have seen before, such column operations, they might change the minors, but they change all of the minors by the same constant factor. And so the entry of this projective space would not be changed by such a change of basis. And so this was just the overview of the definition of the Plücker embedding, and then we're going to see that it represents the Grassmannian as a closed subset of the target projective space.